Hi friends, welcome back to our control system session. The third in the series, we'll be discussing on mathematical modeling of control systems. We all know by this time that control systems can be represented with a set of mathematical equations, which we normally call them as mathematical model. And these are very useful for analysis and design of control systems. Design of control system means finding the mathematical model when we know the input and the output. So these mathematical models are mostly used by two methods. One is differential equation model and the transfer function model. Let's see the differential equation model, which is a time domain mathematical model of control systems. We normally follow these two steps. The first one is applying the basic laws to a given control system, basic electrical laws, and then getting the differential equation in terms of input and output by eliminating the intermediate variables. Let's understand this with an example problem. We're seeing a circuit, RLC circuit here consisting of resistor, inductor, and capacitor. Now, all these electrical elements are connected in series, as we are seeing in this. Now, the voltage applied to this circuit is VI here, and then the voltage across the capacitor is V0. Now, if we see the same, try to arrange it in a mathematical equation using a mesh equation, we get VI is equal to RI into L of di by dt into plus V0. Now, this will be the mesh equation for this circuit, which we very commonly know. Now, in this, let us substitute I in terms of V0. So, which we get I here is equal to C into dV0 by dt. And then we get Vi is equal to RC into dV0 by dt plus LC d square V0 by dt square plus V0. Now we arrange this equation in the differential order form, d square V0 by dt square plus R by L into dV0 by dt plus 1 by LC into V0. So that is equal to 1 by LC into V0. Okay, we are only rearranging this by dividing everything by LC. That's exactly on both sides we are dividing by LC. Now this equation we are now seeing d square y0 by dt square is a differential equation of the second order. That's how we find out the thing. Then the next one is a transfer function model, which is an S-domain mathematical model of control systems. The transfer function of an linear time invariant system is defined as the ratio of Laplace transformation of output and Laplace transform of input by assuming all the initial conditions 0. If we see this equation further into slightly mathematical model, if x of t and y of t are the input and output of an LTI system, then the corresponding Laplace transformation will be x of s and y of s. So the transfer function is always y of s by x of s. That's the change in output by change in output. That's what we normally call the differential, the transfer function. So if you see the same electrical system as an example with the differential equation, we just got d square V0 by dt square plus R by L into dV0 by dt plus 1 by LC V0 is equal to 1 by LC VI. Now let's apply the Laplace transform on both sides. So we get S square V0 into S here, of S we normally call it, or SR by L V0 of S plus 1 by LC V0 of S is equal to 1 by LC VI of S. So if we further simplify this, we get y by 1 by LC. So S square plus R by L S plus 1 by LC V0 of S we are taking out. That is equal to 1 by LC VI of S. So if we take V0 S by VI of S, because that's exactly what is the transfer function, or change in output by change in input. So we get 1 by LC here divided by S square plus R by L S and 1 by LC. So here for S square we have one coefficient. For R by L we have R by L is the coefficient of S and 1 by LC is the constant. Okay, so this is a governing equation for this, where we see Vi of S is Laplace transformation of the input voltage Vi and V naught of S is the Laplace transformation of the output equation, output voltage V naught. So this equation is a transfer function of the second order electrical system because we have S square. And the transfer function of this is Vi of S tending to, this is the transfer function, 1 by LC by S square plus R by L of S plus 1 by LC and giving to V naught. So V naught of S by Vi of S is equal to 1 by LC. This is the transfer function. Now we'll be seeing in our regular courses how this factor will be useful in studying the stability of the control system in different forms. Okay, so for that, thank you very much for today's thing. Next, we will see the mechanical model of the system or the